This video is related to the Core 1 learning unit of the Storing and Retrieving Data educational module. HATOOK 2 was introduced in October 2013 to address the two main concerns with HATOOK 1 environments, scalability and availability. By comparing the main features of the two releases, you gain an appreciation for how HATOOK has evolved over time, by providing new capabilities to meet new demands. For these reasons, the differences between the two architectures will be highlighted. The big difference between HATOOK 1 and HATOOK 2 is YARN. YARN is an abbreviation for Yet Another Resource Negotiator. HATOOK 1 is merely a combination of HDFS and Java-based MapReduce programs. In HATOOK 2, YARN sits between the HDFS layer, which in turn rests on native server storage, and processing frameworks such as MapReduce and Spark. YARN is in charge of cluster resource management and scheduling. In HATOOK 1, MapReduce is really the only processing framework you could use, and it interacted directly with HDFS. In HATOOK 2, MapReduce performs data processing in a fashion similar to that in HATOOK 1. So, which HATOOK component performed the cluster resource management and scheduling tasks in HATOOK 1? MapReduce performed the double duty of both data processing and cluster resource management. HATOOK 1 used MRV1 and HATOOK 2 uses MRV2, that is YARN. In HATOOK 2, there's a single global resource manager process that manages resources across the cluster, and it runs on a master node. The worker nodes will all have individual node managers that perform data processing tasks. In HATOOK 1, there was a single job tracker process that managed jobs. Each worker node ran a node-specific task tracker process that actually executed the jobs. The job tracker in HATOOK 1 performed both scheduling and task management functions. In HATOOK 2, the job tracker functions have been broken into two: scheduling and resource management, with the resource manager handling the scheduling portion and the application-specific application master taking care of resource management. The resource manager in HATOOK 2 manages several key functions previously performed by the job tracker in HATOOK 1. To be more precise, the resource manager performs some of the old job tracker's tasks, and the new application-specific application master takes care of the rest of the job tracker's duties. In HATOOK 1, the job tracker was overwhelmed in a busy cluster, because of its heavy workload in managing both resource management and job scheduling. The separation of the twin key functionalities of the job tracker, resource management, and job scheduling monitoring, lets dedicated daemons relieve this workload pressure. The node manager in HATOOK 2 performs all the tasks previously taken care of by the task trackers running on each node in a HATOOK 1 system. The node manager processes run on the worker nodes in a cluster and serves as an agent that monitors the processing performed on the nodes. The resource manager is a pure scheduler in HATOOK 2, and there's no special linkage between it and MapReduce jobs, whereas in HATOOK 1, the job tracker and MapReduce were tightly coupled. HATOOK 2 has strong high availability features and lets you run both a standby name node as well as a standby resource manager, both of which are critical to the functioning of a cluster. In HATOOK 1, the name node was a single point of failure. If the name node server became unavailable, the whole cluster would become inoperable, as all access to HDFS would be cut off. In HATOOK 1, you could use just MapReduce as the processing engine, regardless of whether you used Java-based MapReduce programs, Pig, Hive, or a streaming model using Python, Ruby and so on. There simply was no alternative execution engine available. HATOOK 2 offers a wide variety of processing engines, such as MapReduce, Apache Spark, Apache Tez and others. Instead of being able to support only batch processing, HATOOK 2 supports a wide variety of applications, such as batch processing, MapReduce and Hive, Pig, Apache Tez. Interactive SQL, Apache Tez. Online database, HBase. Streaming, Apache Storm, Apache Spark and Apache Samza. In-memory, iterative applications Apache Spark. Scalable search, Apache Solr and so on. MapReduce, while it performs several types of work admirably, isn't ideal for all types of big data use cases. One of the big complaints about MapReduce is the high latency of jobs. Hadoop 2 lets you choose an appropriate processing engine for specific types of use cases. Hadoop 1 was limited by its batch processing orientation, where time latency wasn't an issue and where you needed vast amounts of data to be processed. While Hadoop 1 was very good at processing large unstructured data sets containing even petabytes of information, it wasn't deemed to be very useful in the real-time analysis of live data sets. Yarn, MapReduce Next Gen or MRV2, in Hadoop 2 marks a fundamental difference in how Hadoop performs its essential work. Yarn is designed as a general-purpose, distributed application management framework and not as an all-in-one resource manager and performance engine as MapReduce was in Hadoop 1. In fact, quite frequently, Yarn is referred to as the operating system for Hadoop because it performs functions such as maintaining a multi-tenant environment by running batch, interactive and real-time processing engines that can all simultaneously access the same HDFS data. Managing and monitoring application workloads. Apache Hadoop MapReduce, MRV2, in Hadoop 2 retains its processing capabilities and becomes a pure distributed application framework. Initially, Hadoop didn't have a very sophisticated way of allocating resources among the various jobs running simultaneously in a cluster. It used a first-in, first-out, FIFO, model of resource allocation by default, which meant that long-running jobs, by hogging the cluster's resources, could potentially keep small but critical jobs from starting, even when the long-running jobs were non-critical in nature. Hadoop later on introduced much more sophisticated job schedulers, named the Fair Scheduler and the Capacity Scheduler. Just to highlight, that Hadoop 1 uses slots to manage resource allocation, instead of using resource containers as Hadoop 2 does. Fair scheduling is a method of assigning resources to jobs such that all jobs get, on average, an equal share of resources over time. When there is a single job running, that job uses the entire cluster. When other jobs are submitted, task slots that free up are assigned to the new jobs, so that each job gets roughly the same amount of CPU time. The Capacity Scheduler is designed to run Hadoop MapReduce as a shared, multi-tenant cluster in an operator-friendly manner while maximizing the throughput and the utilization of the cluster while running MapReduce applications. These figures depicts cluster utilization over time when running a large job and a small job under the FIFO scheduler, Scheme 1, Capacity Scheduler, Scheme 2, and Fair Scheduler, Scheme 3. The difference between schedulers is illustrated in these figures, which shows that under the FIFO scheduler, Scheme 1, the small job is blocked until the large job completes. With the Capacity Scheduler, Scheme 2, a separate dedicated queue allows the small job to start as soon as it is submitted, although this is at the cost of overall cluster utilization since the queue capacity is reserved for jobs in that queue. This means that the large job finishes later than when using the FIFO scheduler. With the Fair Scheduler, Scheme 3, there is no need to reserve a set amount of capacity, since it will dynamically balance resources between all running jobs. Just after the first, large, job starts, it is the only job running, so it gets all the resources in the cluster. When the second, small, job starts, it is allocated half of the cluster resources so that each job is using its fair share of resources. Note that there is a lag between the time the second job starts and when it receives its fair share, since it has to wait for resources to free up as containers used by the first job complete. After the small job completes and no longer requires resources, the large job goes back to using the full cluster capacity again. The overall effect is both high cluster utilization and timely small job completion. In the Core 1 learning unit, the architectural differences of Hadoop 1 and Hadoop 2 were presented. The big difference is YARN, an abbreviation for the term yet another resource negotiator, which is frequently referred as the operating system for Hadoop. YARN was introduced in Hadoop 2 to improve the MapReduce implementation, but it is general enough to support other distributed computing paradigms as well. Hadoop 2.0 overcomes the single point of failure shortcoming by providing support for multiple name nodes. The main motive of the Hadoop 2.0 high availability project is to render availability to big data applications 24/7 by deploying two Hadoop name nodes, one in active configuration and the other is the standby node in passive configuration. Hadoop 2 supports a wide variety of processing engines such as Spark, Tez, Storm, and others and allows to choose an appropriate processing engine for specific use cases. Finally, the available scheduler options were presented, that is FIFO, capacity, and fair scheduler. The FIFO scheduler has the merit of being simple to understand and not needing any configuration, but it's not suitable for shared clusters. Large applications will use all the resources in a cluster, so each application has to wait its turn. On a shared cluster it is better to use the capacity scheduler or the fair scheduler. Both of these allow long-running jobs to complete in a timely manner, while still allowing users who are running concurrent smaller ad hoc queries to get results back in a reasonable time. This is the end of Core 1 learning unit. Thanks for watching this video.